There we go, sorry about that. I had an issue, and then when I was finally got the stream online, I had another issue that came up. The first one was technical because YouTube. The second one was cat. My cat has allergies, I guess, and she came up and I was cleaning out her eyes, so don't worry, I wasn't digging around. I was using a Q-tip to get eye goop out of my cat's eye. I would much rather have been here, but here I am, so welcome back to Chem 161 with that introduction. We're going to continue talking about electron configurations and talk about atoms that come beyond, where did we stop? Argon, probably, right? Because, as you can see by this weird diagram on the screen here, something kind of interesting happens once you go past 3p. And it has to do with a property that, unfortunately, your textbook doesn't really talk about. But I'm going to talk about it a little bit anyway. You're just not going to be tested on it. For administrative stuff, there's a lab next week. It's lab number 3. I actually kind of want to talk about lab number 3 for this class. Give me a second. I didn't actually prepare this, so... I mean, if it's the lab that I'm thinking of. Yeah, I believe it is, actually. Oh, no, it's not. It totally isn't. Okay, never mind. It must be lab number 4. Okay. Yeah, lab number 3 is a different spectroscopic technique that is useful. Where is the one that I am thinking of that deals with this? It might be number 4. Oh, it is number 4. Okay, so we'll talk about it later. Lab number 3 is pretty self-explanatory. It's just a solution preparation and concentration. You do have to make a graph, though. So if you have issues making the graph for the Beer-Lambert plot, let me know. I can help you with that in the Discord channel. But I'll be due next week. There's very little that I can really talk about because the Beer-Lambert thing is just, it's a linear equation and it's generally just taught in a worksheet or in an experiment on its own. So I'm going to let you just read the documentation and then ask me any questions you might have. Because I can't really anticipate where the problems would be. It's pretty straightforward. It's just, hey, how much light does this thing absorb? We can plot that versus concentration on a graph. And it's linear. So, yeah. If that comes up and is an issue, let me know. Lab number 4, I definitely want to spend some time on because it requires programming in Excel. And depending on where we are in the class, like I might just either spend 30 minutes showing you how to do that during a lecture, or I might just post the video to where I taught it in a previous lab. But in any case, we'll talk about that one when we get there. This one shouldn't be so bad. Okay, so we'll go back to here. All right, here we go. On Tuesday, I gave this to you, this diagram here. It's kind of zoomed out, actually. We'll just go down here. Actually, let's start up here, because this is how we generated that diagram. We did every possible quantum number combination of n, l, and m sub l that we could think of, following the rules. So if n equals 1, l equals this, m sub l equals that, so on and so forth. And we assigned orbitals for all of the possibilities for m sub l for each entry. And we got a bunch of orbitals. And then I said, okay, we're going to arrange these in terms of energy, increasing energy. And we got this diagram like this. Now, for our diagram, this is accurate, except there is an issue. And the issue is that I don't have my pen. Oh, it's on this side of my phone. That's weird. I couldn't see it because it was hiding behind my phone. All right, the issue is that 4S actually shows up here, which is why I have this kind of obnoxious gap between 3P and 3D. And the reason for that is because of some strange phenomenon that have to do with this phenomenon called electron penetration. And your textbook doesn't really talk about this, but I'm going to go over to a different diagram here. We're going to just draw this really quickly again. Wow, that was like the straightest line I've ever drawn. I'm going to try and draw these a little bit off from each other. Wow, what happened there? Undo. Undo. That one could be better. And there's a reason that I'm drawing these a little bit off from each other. So we said earlier that this was true. My pen is not behaving here. That we could arrange our orbitals like this. SPDF. S is the lowest in energy, P is lowest in energy, D is lowest in, and so on and so forth. Now, this diagram here, where I just have the N lines, this is the Bohr model that we started with, right? What we actually do is we put the highest energy that's possible on this line. So for this, it would be 1s. So 1s would be on this line right here. For this one, it would be 2p. And then 2s would just be a little bit below it. Up here, 3d would be on this line. And then 3p would be below that. And then 3s would be below that. And then over here, 4f is on this line. And then 4p would be below that. Or sorry, 4d would be below that. Then 4p. And then 4s. Now, I have not drawn this correctly, but what you're probably noticing is that, actually, you know what I can do? I could do this. I'm going to be sneaky about this and actually put it at the right energy. There we go. So, the reason that these orbitals look like this, where S is lower in P than lower than D, which is lower than F, is due to that phenomenon that I mentioned there, electron penetration. The gist of electron penetration is, due to nodes, there is a probability that your electrons will be closer to the nucleus for the S orbital than for the P orbital. And because your electrons can sneak past the nodes and then be closer to the nucleus, they're lower in energy. And so we rate them slightly lower in energy. Now, your textbook doesn't really talk about this at all. I think there's like a sentence about it. The previous textbook that we had talked about it a lot. But suffice it to say is that because of the radial nodes that are present, anytime your electrons can get closer to the nucleus, they're lower in energy. So we saw that 4s had tons of radial nodes, so you could get real close. You could sneak past the first node, you're kind of close. Sneak past all 3 nodes, you're real close to the nucleus. So it's lower in energy. But as a result of this, if I were to take this line tool here, I know where the line tool is because I use this all the time. There we go. And I go like this. Look where it ends up if I make this horizontal. I'm trying to make it actually 180 here. There we go. Now, my intent was that it would go between 3p and 3d here, but because of the effects of penetration, here I'm just going to hit enter on this and we'll just leave it there. I got to click over there. There we go. So, because of the effects of electron penetration, some orbitals end up lower in energy in higher ends than in the previous n. So 4s is actually lower in 3D because n equals 3 and n equals 4 are so close together that the effects of electron penetration cause our orbital energies to drop below where 3D is. And this happens for all the n's past n equals 4. N equals 5, n equals 6, n equals 7. Because if you remember, if I go back to this screen over here, and I show you this, remember this is how we drew all the principal quantum numbers for our diagram. Way back when we talked about the Bohr model, right? 1 was real low, then 2 was way up high, then they all sort of jammed together as they approached n equals infinity. These lines here are just the n levels, which would be whatever the highest orbital is for that n. And there's not much space up here, is there? Like, it's real crowded. So anything dropping will cause all these energy levels to just get scrambled together. And the order that they end up sorting out to is what that crazy diagram that I just had shows. So this is called the Aufbau principle. Aufbau is German for bottom to top or filling up or something like that. And so the way that we create this diagram, because this is helpful for you to... Oops, that's not the button I meant to push. The way that we create this diagram here, we just draw on this page, that's fine, is you want to list out all of your s orbitals in a column. There isn't an 8s, but that's okay. And then we'll do that for p. There's no 1p. It's not 2p. And then we'll do d. I messed up with my pen there. That was my fault. And then we'll do F. And that's really good enough because it doesn't go much further than that. And then here's what we do. We just start at the top and we start going like this. And every time I pass through, I hit as many as I can. And the order in which... Oops. Sorry, I went a little too low there. The order in which I hit the orbitals is the order of their energy. So I'd start at 1s, then 2s, 2p, 3s, 3p, and then after 3p I hit 4s. And then after 4s it would be 3d, 4p, 5s, and then what comes after 5s? Well, it's 4d, 5p, 6s, 4f, and then so on and so forth until you fill your diagram. So you can create this diagram, and in fact, on the test, when I did this in person 2 years ago, students would always just draw this diagram. They'd draw the Aufbau principle immediately. And it's a good diagram to write. So this is how you create this diagram and know the order of the orbitals. All right, any questions on making the diagram, let me know. All right. Here is a pictorial diagram of that orbital spreading that I was trying to draw. This has arranged the s orbitals all on the left, all the p orbitals in the middle, and the d orbitals on the right. But you can see that going from lowest energy to the highest energy, it does something like this: 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, and so on and so forth. So it's just literally what's the next energy up from this. So now that you know the ordering of the energy levels, you can write an electron configuration for any element on the periodic table. So let's start with zinc. So I want you to write out the electron configuration for zinc. Don't just copy it off of p-table, but do use p-table to count how many electrons there are. Hint, I'll just tell you if you don't want to look it up. Zinc has 30 electrons. I'm double checking that. I thought I knew it, and then I was like, wait, is it right? Yeah, it's 30 electrons. Okay. So go ahead and write out that electron configuration. We'll go over the answer in just a bit. All right, one more minute to enter your electron configuration in the chat, and then we'll go over the answer. All right, let's go over the answer here. So first of all, let's use the alpha principle, which is on the... Well, I drew it, so we'll just go over here, I guess. So I need to use 30 electrons. I'm actually going to write up here. I just want the alphabet principle on the screen here. And so all s orbitals have 2, so I'd go 1s2, 2s2, p orbitals have 6, 2p6, 3s2, 3p6. How many have I used? 2, 4, 10, 12, 18, 4s2, that's 20. What comes after 4s2? It's 3d10, and that holds 10. That's all I need. So 10, 12, 18, 20, 26, 28, 30. So that would be the electron configuration for zinc. There you go. So that's not so bad. We can do that. How much of a jerk can Professor West be, though? Oh, he can be a jerk. Here you go. Here's the next question. Remember when I said you're going to write the electron configuration for uranium? And you're like, no, nobody would make us do that. That's ridiculous. Well, this is that part. What's the electron configuration for uranium? So there you go. I'm going to let you type it out. And I do want you to try and do it. Do it by hand, because you'll never have to do it by hand again after this. But then you can check your answer on p-table. Actually, don't check your answer on p-table, because apparently there's an exception. But we're going to assume that there's not an exception. In fact, it doesn't fit on p-table. It just gets... I had to highlight over it. And you're going to see why it doesn't fit. But go ahead and do this based on the alpha principle. I'll give you 3 minutes to do it. Don't type it in the chat. You'll be typing all goddamn day. And then we'll go over the answer. All right, one more minute to write out the uranium hell, and then we'll go over the answer. All right, so this, we just have to use up all, is it 92 electrons? Let me get my periodic table out. Yeah, 92. I was a uranium chemist. I should have that memorized. Well, I mean, I did say 92. All right, so let's see here. So uranium would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. And then what comes after 4p6? See, I always have to look at this chart because I always think I have it memorized, and then I'm like, oh, what was the next thing? So 4d10, 5p6, 6s10, or 2, 4f14. So in F orbital, there's m sub L all the way from -3 to +3. So that'd be -3, -2, -1, 0, 1, 2, 3. So 7 orbitals times 2 electrons per orbital is 14. And then 5d10, 6p6, 7s2, 5f. You know, I'm going to run out of electrons here at some point, so hold on. 2, 4, 10, 12, 18, 20, 36, 38, 48, 54, 56, 70, 86, 88. How many more do I have? 4. 92. There you go. Isn't that freaking obnoxious, right? Yeah, like, this is stupid. So let me erase all my text here. And then I'll just do... Like, that's obnoxious. Like, no, nobody wants to do that, right? Why? Why do we have to do all of these letters? Well, we don't, so... I'm gonna... Oops, let me go back over here. So, we're gonna pretend that you can do this, but I don't want you to have to write all of these out, because it's gonna take you a lot of time. What I'm trying to get at is, there's gotta be an easier way, right? And there's totally an easier way. So what we're gonna do is, normally I would have you write all of these out and have these really long and obnoxious electron configurations, but we've already spent 30 minutes really just doing 2 examples, so we're going to go just to the next part. Let's cheat. Nobody wants to do this the hard way, right? So work smarter, not harder. Here's what we're going to do. I'm going to write out, as an example, the electron configuration for barium, and it's all of this nonsense, right? So I would go all the way from 1s all the way up to 6s. But there's an easier way to do this. And that easier way is if I go like this and I look at xenon, and then I compare that to where barium is. So this right here that I'm going to box in, this is just xenon, isn't it? And so what we're going to do is we're going to call this the noble gas shortcut. And so you can think of the noble gases on the periodic table, for electron configurations anyway. You can think of them as checkpoints. And the checkpoints basically tell you, okay, once you pass this point, you can use it as a noble gas shortcut. Now, you could do this for helium. It's kind of silly to do that, because writing out the helium brackets is probably more characters than it's worth. But anytime you have a noble gas in your element's electron configuration, you could write that as a shortcut. So for barium over here, I could just say that, okay, well, here's all my xenon. That's this right here. So I'm going to substitute. And there you go. That's way easier, isn't it? In fact, my slide says so it must be true. So that's what I want you to do for the actual exercises, because these are the same examples that we had on the previous slide that I didn't make you do. Now I want you to do them, but you want to use the shortcut. You can ignore this part that says except XE because you don't want to write an electron configuration shortcut for xenon. For what it's worth, if I did ask you this question on the exam, you cannot just do this. That is not valid. What you'd have to do is you'd have to go to the previous noble gas and then keep going from there. Okay? So that's what's intended by noble gas shortcuts. It's a checkpoint once you've passed it, not if you stop on it. So you cannot say xenon equals xenon. But to avoid that problem, I just don't ask you the electron configuration of noble gases. I ask you other elements. So here are 4 other elements. We got germanium, mercury, dubnium, which is like one of the new ones. Dubnium is 105. And then cesium. So write the electron configuration for all these elements using shortcuts. And I do want you to type these in the chat once you get them. I'll number them 1 through 4. Although, honestly, if you put the element name in square brackets and then an equal sign, I'll know what you're talking about. All right, see you in about 5 minutes. 1 or 2 more minutes. Go ahead and type your answers in the chat once you got them. All right, let's go over the results here. I gotta minimize all these windows that I have in the way. I could just write here. Yeah, this will work. Okay. So, I have to find these elements on the periodic table. So here's germanium. So the one that comes before germanium is argon. And after argon, we have 4s2, 3d10, 4p, 2. All right, mercury. What comes before mercury? That's xenon. And that is 6s2, 4f14. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. 5d10. And then whatever the hell this is. So we got radon, 7s2, 5f14, 6d, 1, 2, 3, 3. There we go. And then finally for cesium, that's just xenon 6s1, I think. There you go. So that's all there is to that. And once you get the shortcuts down, this isn't too bad. So what can we do to make it worse? Well, there's some exceptions to these rules. And then we're going to make ions out of them, so we're going to have to remove or add electrons, and that changes the electron configuration. Yeah, that sounds like a problem for future S, right? Well, that's going to be future S in about, say, 10 minutes. So let me clear this. I'll start the timer. We'll take a break, get your water, pet your cat, or just kick back to some more depressing Fallout music that I really love for some reason. There we go. That's where I wanted to be. I'll turn this down. Okay, so the next little thing that we're going to talk about, we're going to try and organize our electrons into our valence electrons and core electrons. In Chem 140, we talked a little bit about valence electrons and how they're the electrons on the outside. Now, on the screen, I have the actual rules for valence electrons. These are just way too complicated, though. And so what I'm going to do is I'm going to just go like this. Because what this is trying to do on the screen, and this is from your text, so it's still valid. These rules are for basically 300 level chemistry. So like me as an inorganic chemist, I would use these rules. And I would calculate which electrons are valence electrons a little bit differently because I care about valence electrons in transition metals and intertransition metals and stuff like that. But here's what we're going to do. The valence electrons, we're going to simplify this. And here's the rule you want to know, because this will make our lives so much easier. Highest N valence electrons. And that's it. Now, what that means is that because I'm giving you a different rule for valence electrons, some of the answers in the textbook aren't going to match up. So like if the textbook asks you, how many valence electrons does nickel have? The answer I want you to say is 2, not 12. Okay? And the reason that the book says it's 12 is because of this right here. Well, transition metals have d electrons. We're going to count these as valence electrons. No, we're not. We're not going to count them as valence electrons. Just ignore them. You're going to count the highest N, and that's it. For our purposes, that's good enough. All right, so let's put that into action here. I don't know why all of this showed up at once, but that's okay. So if I look at fluorine, fluorine's electron configuration is this: 1s2, 2s2, 2p5. What's the highest N? The highest N is N equals 2. So these are my valence electrons. Now, also in Chem 140, we told you the shortcut. You can count the number of valence electrons in an element if you use the ones digit on the group number. So let's get p table up here real quick. So that's not p table. That's the music I'm playing. There's p table. Sorry, I thought I had it clicked already. And we'll click on fluorine here. And you can see that fluorine is in group 17. We're going to use the ones digit to tell us how many valence electrons that there are, as long as your element is in one of these squares here. So if your element is groups 13 through 18 or 1 and 2, this rule will work. In the middle, not so much. It doesn't follow this rule. But if you were in my 140, you probably remember I would ask you how many valence electrons does carbon have? Oh, it has 4. And then we could use that to do Lewis structures and stuff, which is actually coming later on in the quarter. But we have done that. And this is sort of where this discussion is leading to. We can count valence electrons by looking at the periodic table for elements that are in groups 1 or 2, or 13 through 18. Or if you're using the old designation, any group that's in group A. But we'll just 1 and 2 and 13 through 18. Now, any electron that is not a valence electron is, by definition, a core electron. Core electrons are buried under the valence electrons. You don't get to see core electrons. They are lower in energy. You only see the outermost electrons. Just like when you look at an onion, you only see the outermost layer of skin. Even though if you peel an onion, you can see that there's bunches and bunches and bunches of layers. And in fact, what the onion does is it's not really layers as much as it's like a giant spiral, right? That spirals towards the center. But to our eyes, it looks like layers, so we'll just treat it like layers, and that's fine. All right, so what I want you to do here is I want you to write up more electron configurations, but I also want you to write them out without using a shortcut. So I've tried to give you elements that aren't like buried under like 70 electrons. And once you've done that, so let's do silicon for an example here. So silicon would be 1s2, 2s2, 2p6, 3s2, 3p2. I want you to circle the valence electrons. So what's the highest n? So the highest n would be 3. So I'm going to circle everything that has n equals 3. And then I'll underline everything else. So this is my valence. And this is my core. Note that for some elements, you may have a region that you circle, and then a region that's core that you underline, and then you might circle it again. So like if you had something like this, like that, here's your valence electrons. It's these right here, and then this is core. So be careful about that. Don't just circle the whole thing. If we were following the rules of the textbook, yeah, you would circle the whole thing, but there's reasons why we're not going to do that that will make it confusing. So for our purposes, this is correct. And when you get to Chem 361, if you ever decide to take inorganic chemistry, they'll teach you the rules again anyway when it's for transition metals, because they all follow different rules anyway. So go ahead and do this for nickel, bromine, and argon, and we'll go over the answers in just a second. Obviously, you can't underline or circle in the chat, but just like type done or whatever in the chat so that I know we're ready to move on. All right, see you in a bit. One more minute, we'll go over the answers. All right, let's go over the answers here. So I'm going to do this on this sheet. Let me just clear this part over here. All right, so for nickel here, we have 1s2, 2s2, 2p6, 3s2. Ooh, that's saying too many numbers, and my pen didn't keep up, and so my brain wrote the wrong number. Where's nickel? 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay. So, what are the valence electrons? Well, it's these, because the highest N is 4. What would the core electrons be? Everything else. All right. For bromine, we have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 1, 2, 3, 4, 5, 4p5. So our valence electrons would be this one and this one. And these would all be core electrons. And then argon, 1s2, 2s2, 2p6, 3s2, 3p6. There's our valence, and there's our core. All right, so again, valence electrons, highest N. Simple as that. That's all we care about. Ignore what your textbook tells you for that part. I realize that I am purposely simplifying, but it's going to make our life so much easier for the rest of Chapter 3 if we just follow those rules. Or follow the rule of highest N. That's all you need to worry about. All right. Let's talk about weird shit that comes up with transition metals, because remember how transition metals don't follow the rules? Yeah, they do other dumb things too. Sorry, my hair tie came out of place. I had to fix that. What sorts of dumb things do transition metals do? Well, the reason that these dumb things are going to come about is that if I draw the electron configuration diagram, I'm going to ignore what's down here, though. I'm going to go like this. 4s, and I'm going to write 3d. These are approximately where their energy would be. So here's the energy for 4s. Here's the energy for 3d. You'll notice that these are really close together. In some certain situations, my electrons will follow Hund's rule, even though there's a gap of energy between here. So for instance, if I look at 4s and 3d in chromium, you would write this out for chromium and think, oh, okay, well, I'm going to get argon 4s2, 3d4. And what that would look like is this. 1, 2, 1, 2, 3, 4. And in reality, here's what actually happens. And this is unique to chromium and also all the elements in this group. So boop, boop, boop. What we observe instead, and I can't click on the thing to change this, is that we get this. Now, why did this happen? Your textbook doesn't really talk about this, but what I will mention is that from higher level chemistry classes, what I can tell you is that when you put electrons into orbitals, they tend to sink. Because electrons are attracted to the nucleus, and the nucleus lives down here, right? Oh, I hit the button on my pen. There we go. So as you put more electrons in an orbital, the orbitals tend to lower in energy. And as it lowers in energy, it becomes closer and closer to 4s, just a little bit closer, so that this works. And in fact, when you fill this with electrons all the way down to 10, the whole thing is actually slightly lower than 4s, which is why the energy arrangement for valence electrons works out how it does. We're not going to worry about the movement of levels, but the consequences of them do take effect. And so here are, let me clear this because a bunch of text is about to appear. Here are the results of those quantum mechanical tinkering of like the energy levels moving and stuff like that. So if you can land on D5, such as like, oh, I have D4, then what happens is I move 1 to here to make it this. The same thing happens if you land on D9. And the reason for this is because of where the energy levels are. If I can unpair my s electrons, then sure. It doesn't cost me that much to move it up slightly into an empty orbital. Or in the D10 case, well, I have electron-electron repulsion. I might as well just shove it in the lowest energy. So, what you need to know is that if you land on D4 or D9, steal an electron from the s orbital and make it a D5 or a D10. So, we don't end up on D4 or D9. These are not things that happen. All right. The result is you get a slightly more stable electron configuration. The electrons are in overall lower energy if you do this. And that ends up if you land on a D5 or a D10. And so remember, to get from a D to a D5, you have to have a D4. And to get to D10, you have to have D9. This is only for transition metals. All the F elements follow their own sort of exceptions. And in fact, it sort of just randomizes what happens down there. So the only groups you're going to ever observe this in are in group 4. Sorry, not group 4. That would be group 6. Because there are D4 electrons. And then we see this again in group 11, where there are D9 electrons. Now, there are other elements that don't follow this rule. They just sort of do whatever the fuck they want to. You don't need to know those exceptions. And in fact, if I give you that element and you just go to ptable and copy the electron configuration off of it, you'll get the wrong answer. On Canvas, I mean. So I only expect that you know the rules for the chromium column, which is group 6, and the copper column, which is group 11. So these follow the D5 and D10 sublevel rules, where we take one from S and we add it to what we have to get to D5 or D10. So let's do these examples. We'll do these together real quick. So molybdenum, for example, its electron configuration is krypton 5s2 4d4, And what you should say is, oh, D4, I got to move an electron. And that would be the electron configuration that we observed for molybdenum. And then for silver here, silver is krypton 5s2 4d9. Oh, look at that. D9 will move an electron from S to D. And there's your electron configuration. Now, cadmium I threw in here just as practice. If you write out cadmium here, you already have 4d10. You don't have to do anything else. You don't move it around. All right. So those are just some unexpected quirks of transition metals. There are other quirks for other elements. We're not going to deal with them because it gets beyond the scope of pattern recognition. And really, at that point, you just have to do the experiment and test to see where are the valence electrons. All right, any questions, let me know. Sorry, I had to mute there for a second. The cat was crawling in the window, trying to knock my fan over. I have a fan pointed outside of my window, and the cat wants to jump on top of the fan, and then the fan falls over, and then the cat could injure herself, and I really don't want that. All right. We've done electron configurations of elements. Oh, sorry, there's a question. Let's see here. Would you suggest in general just finding electron configurations on p-table? So, if you're on p-table, I can actually show you this because I'm playing with it as I do this, just to make sure that because I know that p-table exists now. For the longest time, I didn't actually know that there was this mode. So if you go up here, you can't see my cursor, to electrons. So normally it's here. But if you click on electrons, it will actually show you all this information, and then here's the electron configuration. So you can see that I don't know what Madelung is. I've never heard of that name. But the ordering of energy here in red is our exception. So if I click on chromium, there's the exception that we just talked about, how we move one electron from 4s to 3d. And you'll see that for all of these, it sort of follows that pattern. Tungsten actually doesn't. I'm going to just assume that it does. But it's really difficult to predict. Like, here's ruthenium. Ruthenium is weird. Oops, I didn't actually click on it. Ruthenium moves one over on its own, too. And I think rhodium does as well. So, like, some of these do this. Palladium moves both of its. Like, why would it do that? There are no 5s electrons. And so it gets weird at some point. The problem that you'll run into is that I'm going to just pick random elements, and I'm going to say, don't report weird exceptions. Just do the D4 and D9 rule. So only this column and this column follow these rules more or less. So don't just copy this into your test or quiz, because if it's a weird exception like palladium, I have not programmed it to do that. I'm not testing you on your ability to look up the answer here. I'm testing you on your ability to understand how to write an electron configuration. And if you just copied this for palladium, Canvas would mark it wrong. Because what I would expect is that you'd be putting in krypton 5s2 4d8, because that isn't an exception that we talked about. No, do not. Oh my goodness, my cat. Hold on. Sorry. Okay, I scared her away. Maya just wants to. I think that there are other cats outside. My neighbor told me that, like, she just had her cat had kittens, And her cat like wanders around in the parking lot and outside, and my cats hate other cats, I've learned. So I apologize for the constant interruptions of cats. I got to get this off the screen here. There we go. All right, so this next section, so we've done electron configurations for any element on the periodic table. Now what we want to do is ions. So if I gave you, like, say, oxygen, you can write the electron configuration for this no problem at this point, right? So, like, that's easy. What if I wanted you to do this? What would you do? Well, something obvious thing, right? I have 2 more electrons than oxygen. I'll just put 2 more electrons in, right? And there you go. That's easy enough. Now, obviously, you can't find these electron configurations on p-table because they don't do ions. Or at least I don't think they do. I'm not sure if you can program it in there to, like, do O2 minus or something. If you do, let me know, because, like, I don't think this is cheating if you look it up online like this. If you could find it as a resource and I can, like show other students that, then that's cool. I would like that. Anyway. But anyway, if you add extra electrons, you just attach them to the end of your electron configuration. That's easy. We can do that. We can do anions, no problem. So anything with a minus charge, you're just going to continue adding in electrons. And they go on the lowest level that's available, so the lowest energy orbital. Generally speaking, that's going to be whichever one you're filling. Otherwise, if you had filled the orbital, so like if you had sodium like -2 or something like that, you'd fill your s orbital and then go to the p orbital, and that's fine. So let's put that one in there. What if we're removing electrons? So again, this follows sort of the I'm going to put a loose squiggle through here because this is correct, but I'm going to show you the easier version of this. Once I click on the right thing. So we'll leave that there because we might use it again later. Oops, that didn't even write. Sorry, I'm trying to write slow because I need to reboot the computer. Photoshop is being temperamental today. And then I wrote the wrong ion here. I want the positive ion. I don't know why I wrote anion. It's because I'm being triggered by my cat. I didn't want to write the word cation. There we go. For cations, remove the valence electrons first. Now, those rules that I wrote up there, start with P, then S, then D, then F. That will automatically do that. But remembering that order is dumb. Instead, remove the valence electrons first. So for example, let's do iron. And I'm going to do the shortcut here. So what would that be? Is that argon? Yeah. Don't memorize the periodic table, you guys. Just look it up. I want to say 6, but I never count this correctly. There we go. Okay. So there's iron 2. What we're going to do, or I'm sorry, that's just iron. We're going to do iron 2 for our next example. And we're removing electrons, so let me write in red here. I need to remove 2 electrons. Which 2 electrons do I do? Remove the valence electrons first. What are the valence electrons? They're these, right? So I'll take these 2 away. And there you go. That would be the electron configuration for iron 2 with a 2+ charge. And then, if I had to take away more electrons, like say iron 3, which is super common, there's 3 fewer electrons. If I've already gotten rid of all the electrons in the n equals 4 valence shell, what's the new valence shell? Well, it'd be n equals 3, right? So then I'd take from D. I don't have an equal there. And there you go. So in other words, you just work backwards, but you start at the valence shell and then you take away from, when you get to the next valence shell down, you take away from the highest energy electron there. So I would get rid of everything in n equals 3 before moving on to n equals 2. I'd get rid of everything in n equals 2 before moving on to n equals 1. And then get rid of the 2 that are in n equals 1 and you have no more electrons. So that's how we do cations. Remove the valence electrons first, and then work with what's left, treating everything as the new valence shell. You'll get rid of those until you've taken away all that you need. So let's go back over here. All right, let's do some examples. We already did this example. Look at me choosing examples that I've already... Oh my goodness, I'm the worst. All right, well, I did those examples, so you know them there. I have written this in gray because I wanted you to see that it was missing. But we would not actually write this in here. You would just leave it blank. Or not, I'm sorry, you wouldn't leave it blank. You would just not write it at all. You'd write 3p6 and then immediately after it write 3d6. Now, when you're writing these electron configurations into your quiz and Canvas, which we'll eventually get to a quiz when we're done with this. It'll take a few weeks, but we'll get there. There is a formatting requirement for it. I believe that it is to type in, like, basically what you see on here without a superscript, but to put a space between each of these. I will tell you within the problem where to put your spaces so that it recognizes what you're trying to do. Oops, I didn't mean to go past that. There we go. So what I want you to do is I want you to try and write down the electron configuration for each of these. Now, be careful for some of them. For example, with copper, remember that copper follows the D9 to D10 thing. So do this first to get regular old copper, and then try +1 it and see what happens. And then for the rest of them, it's pretty straightforward. So go ahead and write the electron configurations for these. Don't worry if they're unstable or not, because some of them are unstable. For example, N+ is not stable. B- not stable. Cl2- not stable. You can use the shortcut if you'd like. If you, for the last one, you're actually going to go to the next level. You'll go past a noble gas. Don't write the new shortcut, I should say. Do your shortcut relative to regular chlorine. So in other words, do neon 3s2, whatever. Then change your electron count, and just leave your answer like that. All right, I'll give you 4 or 5 minutes to do that, and then we'll go over the answers together. One more minute, we'll go over the answers. All right, I'm going to go over these answers here. Let me clear all of this real quick. There we go. Okay. So the way that I do this is I write down the electron configuration of the thing that I'm looking at without making the ion. So for sulfur, that would be... Oops, I don't want to equals there. So that'd be neon... Let me just minimize this real quick. 3s2, 3p4, and then I want to 2 minus it, so I got to add 2 more electrons. So this would become a 6. There you go. All right, for copper here, copper would be argon 4s1 3d10, because we'd land on d9, but then we promote an electron up from s to d. And then to make it plus, we get rid of 1 electron. This is the valence shell electron, so we get rid of that one. So we get argon 3d10. All right, calcium 2 plus is argon 4s2. We make it 2 plus, we get rid of 2. So calcium 2 plus is just argon, which you could write as neon 3s2 3p6. That's fine. How about nitrogen? We've got nitrogen is helium 2s2 2p 3. Yeah, I'm gonna make it plus, so we'll get rid of 1. There you go. And again, writing helium in brackets is kind of silly because you're writing more characters than you would write 1s2, but that's okay. Boron, we'll just write it the regular way. So there's boron. I'm going to make it minus, so I'm going to add an electron. There we go. And then for Cl2 minus, we'll go neon 3s2 3p5. I need to add 2 electrons to it, so I'm going to add 1 here. It can't hold 2. It can only go up to 3p6. And I had to add this in too. And there you go. We can all write electron configurations. Hooray! Now you can do it for ions. So you can write the electron configuration for anything I can come up with in this class. Oh, excellent. Okay. That's it for that section. Any questions? Let me know. All right, we only really have 10 more minutes. But this is really the last section of quantum mechanics. And it's sort of the meat and potatoes behind everything in terms of the effects that we've seen. Because we're going to talk about one very important phenomenon called Z-effective. And it's going to govern all of the different traits and observations that we make here. So The good news is we're getting to the end of chapter 3. We're all sick of being here, I'm sure, because it's this is the end of 2 weeks on it. We're going to spend one more week probably finishing off the chapter, but this is the last of the important sections in this chapter. The last two are pretty much just like gimmies. So let's start talking about this. I'm going to introduce Coulomb's law, and then we'll probably be done for the week at that point. First thing we want to define is the atomic radius of an atom. If you have two atoms that are bonded to each other or are adjacent, the atomic radius is half the distance between those two atoms. Excuse me. Now, if atoms are bonded, they're going to have some overlap, and we ignore that. We ignore the fact that they're overlapped. We just say, okay, the distance between these two would be half of the bond distance, so this is the atomic radius. It's also called a covalent radius if molecules are bonded. But as far as I'm concerned, these terms are more or less interchangeable for our purposes. Just because we don't really find monatomic matter very often. You're not going to find individual Br atoms, so that little bit of extra distance you'd get from where they aren't overlapped, we don't care. What we do care about is how big are atoms in general compared to each other. And so when we do that, we need to consider some different features of them. Some features will make atoms seem bigger. Other features will make them effectively smaller. And so those features are how many energy levels, this is N, have electrons. Well, if you have more N's, the atoms get bigger because the electrons fill shells kind of like an onion. How many layers of onion skin do you have on your onion? The more there are, the bigger the onion. With atoms, it's the same principle. The more layers of electrons you have, the bigger the atom is, because those furthest electrons are farther away from the nucleus than the closer ones. Now, this new topic that we're going to include here, I'm going to actually highlight this one. Effective nuclear charge is a little bit different in terms of what's going on. So, nuclear charge, that's pretty straightforward. This is the positive charge from the nucleus. And so you would say, okay, well, how many protons are in the nucleus? That would be Z, right? Remember when we were writing isotopes for things? We'd write Z and A. Z is the number of protons. It's the atomic number. But what we're going to introduce is the concept of effective nuclear charge. And we're going to add, you know what I should do? Hold on. Let's make that a different color so you can see what I've changed here. We're going to add this caveat. The effective nuclear charge is what outer electrons can feel. And to illustrate this, let's draw a little diagram. So let me erase this. Oh, I erased the alpha principle. That's okay. I'm going to draw a little caricature. So we've got, in our nucleus, we've got some protons here. And there are neutrons, but we don't really care. All right, so I've got 11 protons in the nucleus, because this is sodium, I guess. I don't know. All right. If I was going to draw my electrons, so here I'd have n equals 1. And there are 2 electrons in n equals 1. And then I have n equals 2. And there are 8 electrons here. We're not going to really worry about what orbitals they're in, just their energy levels right now. And then we have n equals 3. Now, the nucleus pulls all the electrons towards itself, right? It doesn't matter where they are. But electrons repel each other, right? And so these electrons on the inside all push against this electron that's on the outside, and the electrons that are on the inside do the same to each other. What ends up happening is that the effect of everything that is closer to the center... Wow, my dotted lines really didn't work. It really did not like that. Sorry. There we go. If you're an electron on the outside, so that would be this guy right here. What you see when looking at the nucleus is a bunch of electrons standing in your way that filter the effect of the charge. In other words, this electron feels 11 protons pulling it inward, but it also feels 10 electrons pushing it away. And the end result is, well, if I just sum them together, it's like that electron feels only one proton pulling it. And this we're going to call Z effective, or effective nuclear charge. And the way that we calculate Z effective is by using this formula. Z effective equals whatever Z is for the atom you're looking at minus any core electrons, where S stands for shielding or screening or filtering or whatever you want to call it. So that's all the time that we really have. We're going to take this equation and put it into Coulomb's law and show how do things attract to each other. They follow this principle. Z effective is the effective nuclear charge that the outer electrons feel. Now, you can calculate Z effective for anything. It does not have to be just valence electrons. It could be whatever electrons you want to. So, for example, if I wanted to do this electron and say, what does it feel? My Photoshop is just dying here, apparently. So it'd be Z, which is 11 protons, minus any electrons that are considered core relative to that. So that'd just be these two, right? So these electrons in the middle here feel the force of 9 protons pulling on them. But because there are 8 other electrons in the way here for this outer one, this one only feels 1. I realize you can't quite see my calculation there. There we go. So you can figure out Z effective for anything. Z effective for the innermost electron will always just be how many protons. So for example, this one right here in the middle, it feels the full 11 protons because there's nothing between it and the nucleus. So the number of shielding electrons would be 0. But as you add extra layers, the core electrons get in the way, and they shield out the effect of the nucleus for the outermost elements. Okay, so with that in mind, I do want you to review the idea of Z effective so that when we come back on Tuesday next week, we are all refreshed and have a good idea of this, because Z effective is going to be one of the most, if not the most important concepts in quantum mechanics. Z effective pretty much tells you everything you would ever want to know about quantum mechanics. So we're going to use it a lot. All right, that's all I got. Yeah, no real upcoming assignments. Lab number 3 will be due next week. That's really all I have. Lab number 3 is pretty self-explanatory, but if you do get stuck on it, please let me know in the Discord. Happy to help you with that. We'll just play this music then. Yeah, have a wonderful weekend. Hopefully it'll be sunny. I'm so sick of this cold. Where's our spring? Take care.